In today's data-driven world, innovation and data integrity are the drivers of success. At Infineon, we believe this is only possible when high-performance components are delivering the highest levels of reliability. At almost every step in the digital and the analog world, we generate data that our devices collect and analyze. With a growing global population, faster digitalization, higher connectivity requirements, and huge amounts of collected data, the demand for reliable and sustainable data centers is greater than ever. Improving their overall energy efficiency not only reduces cost, but also has a positive impact on the environment. The role of data centers in our lives is evolving. Because of digitalization and the ongoing push for artificial intelligence, they'll need to provide more services to more people. This will require a vast amount of information transfer, driven through both regional data centers and edge computing. To meet these demands, Infineon offers market-leading DC-DC converter solutions that support quick design-in options while providing superior efficiency, power density, and robustness. We offer flexible digital controllers with a superior transient response. Over 1 billion of our best-in-class power stages were sold into high-reliability, high-efficiency systems. They integrate Infineon's MOSFETs and can optimize total system solutions from DC to V-Core. Our smart and high-efficiency POL converters are designed for smart enterprise systems. We provide you innovation for best-in-class efficiency, telemetry, transients, design flexibility, and robustness. With our semiconductor solutions for data centers, we're also contributing to a greener and better planet. Part of your life, part of tomorrow. Infineon.
With 5 sections. First, let me introduce myself and my lab. Second, I will explain what a DC series arc part is. Third, I will describe the arc fault detection algorithm based on the signal processing. And first, I will discuss about the arc fault detection algorithm based on the power electronics. And last is the conclusion. I achieved my doctoral degree in the Ulsan National Institute of Science and Technology in 2019. From 2019, I was working in Korea Institute of Energy Research as a senior researcher. In this institute, I researched solid-state transformer, power electronics for modular ESS, and smart inverter algorithms. From 2022, I'm working now in Korea National Institute of Technology as an assistant professor. I published 26 journal papers and 38 conference papers. This is my lab research interest. First is the power electronics with the renewable energies, such as DC optimizer and microinverter. Second is the first diagnosis and prognosis for PV and ESS systems, such as DC and AC arc fault and insulation monitoring devices. Third is the power electronics for the home appliances, such as induction heating. Fourth is the power electronics for the battery cycler and electrical vehicle. And here is, I have a various research fund about the power electronics, and here is my lab members. And now I will discuss about the arc fault conditions. The arc fault can occur when the connector is failure or conductor is broken. In terms of the PV systems, the connector is mostly failured in the power systems. The arc fault consumes the energy which is converted into the light and heat, as shown in these figures. The arc fault can be converted to an heat and light, which induces the fire accident in the PV systems and ESS. Since most of the fire accident by the electrical failure is caused by the arc fault condition, it is very important to detect and extinguish this condition. The arc condition can be classified with the AC and DC arc conditions. For example, the AC arc can be occurred in the AC grid systems widely. The DC arc can be occurred in the PV systems or ESS and DC distributed power systems. In this presentation, we are focused on the DC arc condition. Also, DC arc condition can be classified with the series and parallel arc conditions. Here is the two example of fault conditions. First one is the DC series arc fault condition, and bottom one is the parallel arc fault condition. A series arc fault condition can be occurred when the positive or negative leads are broken or connector is. In the case of the parallel arc fault conditions, can be occurred when the positive and negative are shorted. Therefore, the parallel arc fault induces the very large current flows, which is easy to detect the failure. In terms of the parallel arc fault condition, the fault detection speed is very important. However, the series arc fault is difficult to detect the failure. I will explain next slide. Here is the example of the arc fault systems. It is configured with the AC/DC rectifier and the DC converter. The AC/DC rectifier generates the 380 volt DC link. In these cases, the series arc fault occurs in the DC link side between the AC/DC rectifier and DC converter. The experimental result shows some current drop when the arc fault occurs, and then steady state arc fault condition, the DC magnitude of the DC magnitude of the current is similar with the normal condition. Therefore, the series arc fault condition is very difficult to classify with the normal condition using only the current magnitude. Therefore, some kind of signal processing or the specific technologies are required to detect the series arc fault condition. Here is the UL standard condition. In terms of the underwriter laboratory standards, the series arc fault in the PV system should be detected within 2.5 seconds. This figure shows the energy and time graph for fault detection. This standard covers region A and region B. It requires the various arc fault condition according to the arc fault gaps and the arc fault speed, and the designed arc fault detector should be satisfied this condition with this should be satisfy this condition and should be detected within 2.5 seconds for the PV systems. And here shows the string inverter and DC optimizer conditions. Upper figure is string inverter condition. It is configured with the series connected PV panels. In this figure, each power sources operates as PV panels. The decoupling network and line impedances can be designed to simulate the PV panel operation. In this condition, the series arc fault can be occurs between the PV panels and string inverter. Also, it can be occurred between the PV panels. The bottom figure is the DC optimizer conditions. It is configured with the PV panels and DC optimizer and grid-connected inverter. In this condition, the arc fault can be occurs between the PV panels and DC optimizer. Also, it can be occurs between the DC optimizer and grid-connected inverter. Therefore, various places in the PV systems can be the candidates of the arc fault condition. And this following graph is the statistical data about the fire accidents on the PV systems in the South Korea. It shows that the arc fault is main cause of the fire accident in the PV systems. Therefore, arc fault detection is very important. From this section, the signal processing method for the arc fault detection is discussed. In terms of the this component in the current, the normal and arc fault condition is difficult to classification. Here is two graphs. First one is the normal condition, and bottom one is the arc fault condition. As you can see, the right figures it shows the time domain operation conditions. The right figure, this component has not significant variation between the arc fault and the normal condition. However, in terms of AC component in the current, the arc fault condition can be classified with the normal condition. As you can see in here, the current variation is increases between compared with the normal condition at the arc fault. The large current variation increases the AC component magnitude. The FFT fast Fourier transformer can classify the normal and arc fault condition. The right figure shows the example of the arc fault experimental result from a Texas instrument. It also shows the magnitude difference between the normal and arc fault condition. And here is the experimental setup for series arc fault condition. We utilizes the Regatron PV simulator and Echo's PV inverter. And also the arc fault generator is designed with the US standard. The experimental result shows the small DC link voltage and current variation at the arc fault steady state condition compared with the normal condition. It also shows the FFT magnitude variation compared with the normal condition. And so we should be classify why the FFT can be proper to detect the arc fault condition. So we designed the experimental setup to measure the impedance of arc fault condition. In this experimental setup, the power source is can generate the DC and AC hybrid voltage sources, and arc fault generator and resistor is used to measure the impedance of arc fault condition using the AC perturbation. And here is the experimental result of arc fault impedance ranges. Therefore, frequency analysis is proper to detect the arc fault condition. In this previous research, various fault detection algorithms were proposed. This presentation shows the hybrid fault detection algorithm with the statistical variation and frequency analysis. Here is the right equation shows the statistical analysis. The digital signal processor implements the Gaussian filter for measured signals. From the filter values, the gradient of current is calculated to catch the drastic variation of current. It is designed to catch the momentary drop in this current when the arc fault occurs, which is discussed in the previous pages. Also, we can calculate the moving average and the standard deviation to make the threshold value of the drastic drop of current variation. From the calculated moving average and the standard deviation, the threshold value can be designed to catch the steep current variation. The design freedom of threshold value is alpha. When the alpha value is 5, the steep first current is classified with the 99.9999% normal distribution curve. And here is the experimental result of the steep current variation from the filtered DC current and threshold values. According to the arc gaps, the current variation can be well detected. As shown in these bottom figures, here is the 0.1 millimilli, and here is the 0.7 millimilli. The filtered current value is over the threshold values. However, only the current detection is limited to classify the arc fault condition from the stem load responses and the soft start condition and turn off inverter, and etc. Therefore, additional fault detection indicator is required. Here is the discrete Fourier transform to calculate the magnitude variation in terms of the AC component. The calculated DFT can be formulated to average value for P times. The P value is designed from the designer. The large P requires more time to calculate the DFT. Small p reduces the computation times. Also, the standard deviation can be calculated from the average DFT and DFT values. From the average value and standard deviation, the normal condition can be defined as magnitude references. As shown, we discussed it in the previous statistical analysis. And here is the experimental result at the normal condition and the arc fault condition. The arc fault condition is higher FFT magnitude compared with the normal conditions. At the arc fault condition, the DFT is also calculated. The difference between the DFT and magnitude reference is calculated. The digital signal processor counting the abnormal condition according to the frequency bins. Here is the second equation shows the measured DFT values at the arc fault condition, and here is the reference magnitude we was calculated at the normal conditions. And the DSP counting the number of abnormal conditions, and the number of abnormal condition is higher than the threshold values. We can detect the arc fault condition using the fast Fourier transform. And here is the magnitude references from the normal conditions, and right one shows the arc fault condition result of using the DFT. And here is the experimental result of arc fault condition and stem load responses. First, the arc fault condition is detected with statistical analysis as shown in figure B's. And the filtered current value is higher than the threshold value. It can detect the drastic current changes. Also, the DSP calculate the normal magnitude references, and the DFT magnitude is compared with the magnitude references. And then the DSP counting the magnitude differences, the arc fault condition can be detected. In the stem load responses, it can higher than the threshold value of steep current variation. However, the FFT result cannot over the FFT threshold values. So the stem load responses can detect can pass the steep current variation. However, the FFT can be FFT of the current does not pass the threshold values. So the arc fault condition and stem load responses can be classified. And here is the experimental result. The Regatron PV simulator, arc fault generator, PV inverter, and the arc fault detector is configured for verify the fault detection. First is the normal condition, which does not detect the fault. And in the fault condition at the rated power conditions, the arc fault detector can catch the series arc fault condition within 100 milliseconds, which can satisfy the UL standard 2.5 seconds. Also, the arc fault at the right load condition can be detected with the designed signal processing method. It can classify the soft start condition and turn off of the inverter condition and stem load responses. From those kind of experimental results, the validity of the arc fault detection is verified. However, the limitation however, the limitation of arc fault condition is existed. The high switching frequency noise is affected to the arc fault detection performances. Here, two experimental results. Upper one is the arc fault condition, and bottom one is normal condition. The high switching noises cannot classify the arc fault conditions. The misoperation can be occurred. To overcome those limitations, the arc fault detection based on the power electronics is designed. Here is the arc fault modeling in terms of resistances. The arc fault condition operates as the negative resistances. The increase of current flowing induces the small arc resistance. Also, the decrease of current increases the arc resistances. Therefore, arc fault resistance can be regulated with the current flowing. And here is the electrical PV models. The PV panel shows the increase of PV panel shows the increase of voltage at the small current rating. Also, the increase of load condition reduces the PV voltages. Here is PV systems using the DC optimizers. The arc fault can be occurred between the PV panels and DC optimizer and grid connected inverters. Now we are focused on the arc fault condition between the PV panels and the DC optimizer. So we have to remember the increase of the current reduces the PV voltage, and decrease of the PV current increases the PV voltage, vice versa. And using the arc resistance characteristics and PV voltage characteristics, we can detect the arc fault conditions. And here is the arc fault equivalent model. Here is the PV source voltages and line inductor and line resistance, and the arc fault resistance is added into the power lines between the DC optimizer and PV sources. As you can see in here, left figures, reduces of PV current increases arc resistances. The increase of arc resistance result in the open circuit conditions, which can achieve the arc fault extinguishing and the arc fault detection simultaneously. So here is the proposed arc fault detection and extinguishing method. When the input voltage reduces, the DC optimizer reduces the duty cycle. Duty cycle reduction means the reduces of the processing power. When the arc fault is occurred at that time, the arc resistance increases to the open circuit conditions, and then the arc voltage increases to the input voltage, like as the PV voltages. However, only the irradiance variation of some kind of other factors, the reduces of the power induces the reduction of power increases the PV voltage, as shown in these figures. And then the DC optimizer can figure out the current condition is arc fault or the normal conditions, and then back to the MPPT operations. Here is the simulation model of the arc fault condition using the PV model and line impedances, and here is the arc fault conditions. The arc fault voltage is has variation according to the lookup table. And here is the normal condition. Only the irradiation variation reduces the duty cycle variation, like as the to reduces the power reductions. In the case of the normal condition, increases the PV voltages at the irradiation drops. And then it can return to the steady state conditions after the proposed algorithm. However, in the arc fault condition, the arc fault started in this condition, and then the duty cycle is reduces to find the arc fault condition and then the increases of the arc voltage can operate as the open circuit condition, then the DC optimizer does not operate after the arc fault extinguishing. And here is the experimental setup. Here is the PV panels with the LED lamps and the arc fault generator and DC optimizer and DC load is configured. And the digital signal processor implement the MPPT operation, and also it can operate the arc fault detection and extinguishing. And it operates here is the experimental result. Here is the stem load responses, and it does not detect the fault detection because it is different from the signal processing technology. It does not affected from the stem load responses because the DC optimizer knows the reference variation, and it does not changes the input voltage according to the stem load conditions. And also here is the irradiance variation conditions. Here is the irradiation variance conditions. And when the input voltage drops from the irradiation variances, the fault diagnosis operates, and it reduces the input current like this. And then the input voltage increases for these algorithms, and then back to the normal conditions. However, at the arc fault condition, the fault diagnosis operate like this method. The input current is reduces, and then the input current is reduces with the arc fault diagnosis algorithms. And then the fault conditions, it can be increases the arc resistance to the open circuit conditions. The PV arc voltage is increases up to the PV voltages. It can be extinguished by the proposed algorithms. And then the DC optimizer can figure out this condition is the arc fault conditions. And second method is utilizing the differential power processing method. A previous method used the arc fault resistance characteristics compared with the PV models, and now uses the characteristics of differential power processing modules. The DPP units measures each PV voltage, each PV panel's voltages, and then arc fault can be occurred between the PV panels and the grid connected inverter, and the arc fault can be occurred between the PV panels. The total PV panel voltage should be same as the measured DPP voltages. However, at the PV total voltages can be calculated some of the DPP voltages, and the DC link voltages can be expressed as the PV total voltage minus arc voltages at the arc fault conditions. In the normal condition, should be link voltages, should be total PV voltages, which is some of the DPP voltages. So DPP unit is proper to detect the arc fault condition easily. So here is the control hardware in the loop experimental setups. Here is the 4 PV panels and 4 PV differential power processing unit and grid connected inverters. And yellow line is the DC link voltages, and the blue line is the total PV voltages. When the irradiation changes, the link voltage and the total PV voltage, which is some of the DPP voltages, is same. However, at the arc fault condition, the link voltage and total PV voltage is different because of the link voltage is the total PV voltage minus arc voltages. So it can be easily detected with the relationship of the DPP voltage measuring. And here is the experimental result. We use the two Megatron PV simulators and arc fault generator and grid connected inverters. And here is the arc fault condition between the PV and inverters. And here is the inverter input voltage is reduced according to the arc fault voltages. However, two PV voltages has no voltage drops. Also, the arc fault condition between the PV panels has induces the DC link voltage drops as shown in the right figures. However, the two DPP voltage does not change. So the easy detection method can be utilized to classify the arc fault condition and normal conditions. And here is the conclusions. So in this webinar, I discussed about what is the arc fault condition, and three arc fault detection method is discussed. First one is the signal processing method, and two is the power converter operating algorithms. One is the DC optimizer, and another one is the differential power processing units. And thank you for your listening. And if you have any questions, and feel free to talk to me. Thank you.
Okay, thank you very much, Professor Bass. It's really interesting presentation. Okay, and now we go to the Q&A session. And I have one question from Dr. Yi. Can you directly ask Professor Bass, Dr. Yi?
Yeah, hello.
Okay, please.
Yeah, hello, Dr. Park. Thank you very much for your very nice and informative presentation. I would like to ask what kind of the DC optimizer did you use to implement in the experiment? And
the bidirectional buck boost converter is utilized for the DC optimizer.
Yeah, and also I saw that you can you back to the simulation?
Simulation.
I remember. Yeah, the next slide.
Yes.
Yeah. Because I saw that when we have for example, the drop of the input voltage, it means we have some problem in the PV panel, right?
Yes.
And then we control the duty cycle, right?
Yes.
So how could you please explain more detail in this case? How can we catch the signal? For example, we should use a voltage sensor or some current sensor to detect the error in the input voltage of the DC optimizer here.
This DC optimizer uses the as you know, the DC optimizer has the input voltage and input current sensors. So it has threshold values, like when the arc fault occurs, then the input voltage can be dropped like as 10 volt or 20 volt. So then the this optimizer operate the designed control algorithm to reduces the power processing.
Yeah, and also that you add some component. I mean, you use the ARC fault circuit, right?
Yes.
So I don't know exactly for in practical system, how can they set up this, and did you evaluate, for example, the cost when we add for example, we add the circuit to detection the error, right? And then the converter will be the cost of the converter will be increased. So did you evaluate the cost in this case?
Cost problem.
Yeah.
Actually, we does not consider the cost problem since the designed DC optimizer utilizes the conventional DC voltage sensors, like as the isolated DC voltage sensors, like as
So we just sensing the input voltage, input current, and also output voltage and current, and and then we can apply the control method to detect the error. Is that
yes. Actually, as you know, the DC optimizer is inevitably have the input voltage sensors and input current sensors to implement the MPPT operations. The same input voltage sensors and current sensors is utilized to measure the input current drops. So the cost increase does not occur.
Okay, I got it. Because last time I have implement DC optimizer, but I use the DCS topology. It's a LLC operate at resonant subfrequency. So it's fixed the duty ratio, right? We just boost. Yeah.
Actually, I described the duty cycle, but correct version is the actually power processing.
Okay. I got it. I got it, because you use the buck boost here, so you can control the duty ratio.
Yes, thank you.
Yeah, thank you very much. Yeah.
Okay, thank you very much, Professor Bass and Dr. Ye. Okay, any question from the audience or the speaker?
I have a question.
Okay, please.
Okay, good morning, Professor Park. So Professor Hong Hoa Pyong Park.
Yes.
Did I speak pronounce correct? Yeah. Thank you very much for your nice presentation. I think it's very interesting. So maybe many Vietnamese students are watching now is interesting and want to join your lab. So does you want to recruitment the Vietnamese student?
Yeah, sure. Please send me an email.
Okay, that's very good. I think it's a very interesting topic. And so your presentation now maybe will be replay in the VPEG system, or we will broadcast in the Facebook. Is problem is okay?
Pardon, one more time, please.
Maybe we will broadcast this video in the Facebook or something social network. Is okay?
Social network.
I mean we will record this webinar, and then can we share it to the YouTube or some social media?
YouTube.
Yeah. If you agree, and then we can share. If it's no problem. If
we will have the channels in YouTube, and we after the webinar, if the speaker agree, we can reshare your webinars presentation in our YouTube channel for the audience.
Okay, sure.
Yeah. Okay. Thank you very much. Yeah, Dr. Da, you can reshare the his presentation in our YouTube channel. Yeah, for everybody can reach it, and also for just take the technical content in the presentation. Okay. Thank you very much. Okay, Dr. Da,
Thank you.
Have you any question more?
Okay, I have a question. So
okay,
I see you have asked the generator, right?
Yes.
For generator. So
Yes.
this kind of the machine, we buy this or we create it by yourself? This generator.
Aquapulse generator?
Yeah.
The Aquapulse generator is here is the model of the Aquapulse generator is designed by the suggested by the underwriter laboratories. So we designed the Aquapulse generator by the UL 1699B standard.
It means you design it by your lab or without the
yeah, we have this Aquapulse generator.
Oh, so you design it. So you design this generator, or I mean,
yes.
Oh, really? Oh.
Yes.
Okay.
Sure.
Okay, I understand. And I have another question because maybe I missed something because I'm not familiar with the arc fault detector. So in practical, when we detect this fault and after that, normally we will reconnect or what kind of the action people often do after we detect this fault?
When the arc fault occurs, the arc fault can be occurred by the loose connector or the conductor broken. When the conductor is broken, it should be connected, or conductor should be replaced. And when the connector is loosened, so connector should be reconnected again to eliminate the arc fault condition. Thank you.
Okay, thank you for your answer. I got it. Thank you.
Okay, Professor Bart, can you hear me?
Yes.
Okay. I received a question from the audience. The question is, in the PV solar system, there is usually a Faraday filter. If we use the decoupling network together with the Faraday filter, does the frequency used to detect arc fault have any effect? This means the question is, in the PV system, the Faraday filter is used. If the decoupling network together with the Faraday filter, any effect to the frequency used to detect the fault condition? Yeah. Okay.
You mean the decoupling network?
Yeah, decoupling network together with the Faraday filter. Do you use the Faraday filter in your system? Actually,
we tested with the DC sources with the decoupling network and line impedances. Yeah. Also, we tested with the rear PV panels. This DC sources uses the decoupling network to minimize the effect of the DC sources switching noises or other effects. So the DC sources requires the decoupling networks to decoupling between the DC sources to the inverters. So the module and line impedances is required to operate the DC sources as PV panels. So it also suggested by the UL standard. So it is the proper substitute of the rear PV panels.
Okay. Okay, Mr. Yao, can you hear the answer from speaker? Do you satisfied with the answer? Okay, Mr. Yao, can you hear me? Yeah, okay, he talked the 10 or the answer. Okay, thank you very much. Okay, any question for the speaker?
Could you please for me have a question, please?
Yeah, okay, please.
Yes. Thank you, Professor Park. Have a interesting presentation. I have a question for you. I can see in the Korea, Korea is one of the most country in the world apply DC microgrid in practical. I can see in your presentation there are two methods you apply it in the research. The first one is apply hardware loop, and the second one is apply the hardware. And my question is, what's the purpose of the hardware loop system in your research? I can see in some hardware loop research, we often implement the hardware loop to compare the practical experiment and the simulation result. So what I mean, what is the purpose of hardware loop in your research? Thank you.
You mean the
I mean, what is the purpose of hardware loop in your system?
purpose of this?
Yes, purpose.
The purpose of this converter and algorithms. You're right.
I mean, I can see the hardware loop system in the research. I so confused. What's the purpose of hardware loop?
Purpose in these systems, right? Actually, yes.
I can see that this is a practical system, and I can see another system. There are simulating in the MATLAB program, and you put the program in the hardware loop. And my question is, what's the purpose of this system with the hardware system? Because in my lab in Vietnam, there's a hardware loop system, and we often make a experiment with hardware loop and compare with practical experiment. And from the result, we can see some evaluation. And in the system, I don't have more experience in that hardware loop experiment. So my question is, what is the purpose of hardware loop in your research?
You mean the purpose of the hardware in the loop system, right?
Yes.
Actually, we uses the hardware in the loop experimental setup.
Yes, that's one.
Yes, verify the validity of the voltage level differences. Like as I mentioned that the arc fault condition induces the addition of the arc resistance in the power lines, which increases the arc voltages. It is about the 20 volt, around the 20 volt, 10 to 20 volt. It can be over the 20 volt, but so we have to test the proposed algorithm using the differential power processing units. But before the test in the real practical experimental result, we tested the OpenRT platforms to test it before the hardware test. So yes, just the hardware in the loop test is utilized to verify just before the real experimental result. So since the two verify the detection algorithm, in the digital signal processors. It is interfaced between the operator and the DSP systems.
Okay, I got it. Thank you so much.
Okay, thank you so much. Okay, any question more on the first presenter? Okay, I have two small questions for Professor Bass. The first one, I see your system is applied for the BV system. Yeah, it is effective for BV system. My question is that your proposed methods and system can be applied to other renewable energy system, for example, wind energy system or motor drive system. Is this possible? Is this effective? Okay, please.
The proposed system maybe it should be tested and simulated, but maybe effective to the various applications, since the arc resistance characteristic is same as the AC systems and DC systems. And here is the from the arc resistance characteristics, the power electronics technology can implement the arc fault detection and extinguishing very easily using only the change of the power driving ratings. Maybe, but we have to test it.
Okay. Maybe first we need to test. Yeah, okay. The second question is that's applicable to the slide with the signal processing.
Yes.
Signal processing slide. Yeah. Okay. Here. Yeah, I see you use many signal processing algorithm and also the filter. Yeah. My question is that any delay time between the fault detection and your algorithm delay between the fault detection and algorithm delay because
fault
of
detection.
Okay. Signal processing algorithm. Any delay?
Actually, the fault detection is very significant problem. Actually, since the every inverter has different magnitude and noise magnitude. So the signal processing method should be considered those kind of noises to some kind of the signal processing algorithm should be passes the switching noises, and the bottom level noises is different, all different according to the inverters. So the most of the PV inverter brand makes itself the arc fault detectors, like as HANA solution also makes the arc fault detector for their inverters. Also, Solar Edge also makes their own arc fault detectors, because the arc fault detector is very difficult to generally use.
So
yes, it's a real problem.
My question because that I also study in the harmonic detection system and algorithm to propose the controller to reduce the harmonic distortion. So the delay time between the harmonic detection and also after the signal processing is very important. It takes a lot of time for the delay time. The control system have a not good performance. Yeah. Okay. Thank you very much for your explanation. Okay. Any question more? Might be no. Okay, Professor Park, thank you very much for your very nice presentation and attractive information. Okay. And in the
I have
next
a quick question.
Okay.
Sorry, Dr.
Okay, please.
I know that Dr. Park, you are recruiting the student now. So could you share some information, for example, the admission condition or some how the student can contact you by email or some?
Yes. So if you guys have interested in contacting me, please send me an email, and maybe our university support all the funding for the all the students. I know.
Yeah,
like that
I know that Como Institute is very good support from
support.
Yeah, I know that. I have a friend. He studied in Como, but I don't know exactly the situation now.
Yes, the funding, according to the funding situation, I can just maybe I can funding the for each student. So that does not matter.
Yeah.
And then
So
if you guys are interested, and then yes, please contact. Feel free.
Feel free to contact them.
Yes.
Thank you very much.
Okay, thank you very much. And Professor Bas, the next speaker and next presentation is with the slide in English, but because there are many Vietnamese students here, so the next presentation will be delivered in Vietnamese. Although the slides in English, if you are interested in, you can continue stay here to see the slide only. Because the presentation language in orals will be in Vietnamese. So if you are not inconvenient, you can leave out the webinar and no problem. But of course we are welcome. You continue stay here to see the slide in English. And if you have any question,
I
you
stay
can ask.
Here. Yes.
Okay. Thank you very much. Okay.
Thank you very much.